Assalamu alaikum students. We have done 3 chapters of integral equations with boundary value problems. Right now we are doing chapter number 4, and our first method in this chapter is Fredholm integral equation of second kind with separable or degenerate kernel. In previous chapter 3 we have already done the questions regarding separable or degenerate kernel, but in that chapter we were having the Fredholm integral equation that was homogeneous. That was missing this part of f of x. Right now we have this f of x here. So this is non-homogeneous Fredholm integral equation of second kind. Second kind because we have this unknown function outside the integral as well. So consider this Fredholm integral equation of second kind where kernel of xt, that this k of xt is your kernel. Kernel is summation I is equals to 1 to n fi of x gi of t. Using this value of kernel here in this equation, we will get this equation. We know that our integration is depending upon t. So take this x component function that is depending on x, take it outside. Now we know that whenever we have a separable or degenerate kernel, what we do, we just separate the functions like this. And then after taking the variables that are not taking part in integration, after taking it out, just take this integral as c. So let's take it as ci. Mark it as equation 3 and now write this ci here. Ci is integration from a to b gi of t y of t dt. Mark it as equation number 4. Now I'm going to rewrite this equation 3. We can write this equation 3 as y of x equals to f of x plus lambda summation j is equals to 1 to n cj and fj. We can just change this as well from I to j. Now I'm going to write this equation for variable t because I need here t. So y of t equal f of t plus lambda summation j is equals to 1 to n cj fj of t. Now we are going to use the values of y of x and ci in equation 3. In equation 3, I am putting here the value of y of x and I am using here the value of c of I on the left side and right side as well. So on the left side I have y of x, so use this y of x here equals to this f of x plus lambda summation I is equals to 1 to n fi of x and use the ci here, this integral. Now after using the value of ci, you can see we have y of t here. This is y of t, so this will be f of t. So let's correct it. Here we have f of t. Now, in place of y of t, I am going to use the value of y of t here. After using the value of y of t, you know that inside the integration we have plus two functions. So just split this integral onto these two functions separately. After splitting it, you can see that we can write it as summation I is equals to 1 to n fi of x ci equals to summation I is equals to 1 to n fi of x beta I plus lambda alpha I j ci. I am just specifying their names. I am just letting it as ci, and now you can see that you have here I and j both. So I can take it as alpha I j. I'm just closing it. And whatever I have supposed, just write it here. And I and j can be 1, 2 up till n. Now just expand this bracket like this. After expanding it, move everything on the left side and make it equals to 0. Take summation I is equals to 1 to n fi of x common outside the bracket. So we got this equation. Since these are linearly independent, so this can never be 0. It means this bracket is going to be 0. After taking it equals to 0, just rearrange it and take this beta I on the right side. And let's write some equations, system of linear equations. For I is equals to 1, in place of I, in place of I, in place of I am just taking it 1. Now I am going to vary the values of j. First of all for 1, and then for 2, then for 3. So I can write it as alpha 1 1 C1, alpha 1 1 C1, beta 1 on the right side, and plus, summation means plus, alpha 1 2 C2 plus alpha 1 3 C3 plus up to alpha 1 and Cn, and so on. And after taking it, writing it, expanding it like this, I'm going to combine the constants C1 together, and I'm writing the rest of the constants as this. Similarly, write it for I is equals to 2 and then expand it the same way. And then write it for 3 and then write it for n. So we got a system of equations like this. After getting the system of equations like this, we got d of lambda equals to, we can write here d of lambda, its determinant, for discussing the cases of solution. First column is for C1, second for C2, and up to Cn, which is a polynomial lambda of degree at most n. Again, d of lambda is not identically 0. Since when lambda is 0, then d of lambda will be equals to 1, because this will be an identity matrix, determinant of identity matrix, which is a trivial case. Now here comes situation 1, when at least one right member of the system is non-zero. This is the right member, these are the right members, beta 1, beta 2 up to beta n. If at least one of the right member of the system is non-zero, then these two cases arise. If d of lambda is non-zero, this d of lambda, answer of this d of lambda is non-zero, then a unique non-zero solution of the system exists. So equation 1 has unique non-zero solution given by this equation, your main equation of your y of x. Here, this y of x is your solution. If d of lambda is equals to 0, then the system has either no solution or they possess infinite many solution. Whatever I am writing it here, basically we are going to discuss it in examples as well later on in upcoming lectures. Situation 2 comes here when f of x is 0. You know that this is your y of x equals to f of x plus lambda I is equals to 1 to n fi of x ca. If your f of x is 0, it means if your equation is homogeneous, then equation 6, this equation 6, look at this, f of t is going to be 0 then. So betas will be 0. Shows that beta I is 0 for I of these values, and system reduces to a homogeneous linear equations, and when it reduces to the homogeneous linear equations, these two cases will come as the same. The situation 1, case 1 and case 2, same will be discussed here. Now comes here the situation 3, when you have non-homogeneous, means f of x is non-zero, but this combination gi of t f of x equals to 0, this one, then f of x is orthogonal to all the functions g of t. What it means? It means f of x is orthogonal to gi of t. Then equation 6 shows that all beta i's are 0. If this is orthogonal, then again it's 0, so beta i's will be 0. Hence the system reduces to homogeneous linear equations. And after reducing to homogeneous linear equations, two cases comes. If d of lambda is non-zero, then a unique solution exists. So we will see that we'll get this solution y of x equals to f of x. And if d of lambda is 0, then the system possesses infinite non-zero solution. Then the solution corresponding to lambda are now expressed as sum of f of x and arbitrary multiples of eigenfunctions phi of x. After this, we have done just simple example 1 and example 2. These are the simple one that we will discuss here. And after that examples, the cases will come in the next lectures, in this main one. So don't forget to watch the next lectures as well. But before that next lectures, this is just simple example. Let's do it first. Solve the following integral equations. This is, you can see that your integral is depending on u. So s is irrelevant here right now for integration. So take it out and take the rest of the integral as c. And now you know that c is integration 0 to 1 u squared g of u du. G of u, right now it's g of s. So g of u will be u 1 plus c. And let's integrate it, apply the limits of integration, simplify it, you will get the constant c is equals to 1 over 3. Plug in the value of c here in your g of s. So this is your solution right now. So same, you can see the example 2. You can try it as well at your own. I have solved it here already. You can see here. You can try it at your own. And you can try doing this assignment as well. The same way the examples are done. After this lecture, we will do this example. We'll discuss cases, and we will discuss all the cases in detail in this example. So you need to just watch all the videos so that you can observe how we are going to discuss all the cases.